Introduction to Chemistry. Chemistry is the science that is concerned with the composition, structure, and the properties of matter. All of the objects that we encounter on a daily basis, this would include things like pens, blankets, refrigerators, and all of the things that we encounter in nature, such as plants, animals, streams, and rocks, are all different forms of matter. Now, since chemistry as a science deals with most of the objects that we encounter on a daily basis, it's difficult to exaggerate the influence that chemistry has on modern science, technology, and all of our ideas about our surroundings. When we introduce chemistry, one of the first things that we usually talk about is the scientific method. The scientific method provides us with an overview of the way in which we make observations about natural phenomena and then formulate theories to summarize them. So the scientific method can be broken down into about 4 or 5 steps. So the first thing that we do is we formulate a question. We formulate a question about a specific observation, something like why is the sky blue, or why won't my lawnmower start? Something very simple like that, or it can be something more complex and related to chemistry, like why does an electron behave like both a particle and a wave? Well, so that would be the first step, to formulate a question. The second thing that we do is we formulate a hypothesis. And a hypothesis is just simply a tentative explanation for some regularity of nature. So it's a tentative explanation as to why something is behaving a certain way or why something won't do something. So that's the second step, is come up with a hypothesis, which is just simply an explanation. Now, third, you have a hypothesis, so you need to conduct experiments. And the goal of conducting these experiments is to either prove and or disprove your hypothesis. And then finally, if your hypothesis is proven by experimentation, you can call your hypothesis a theory. And what generally follows is usually more testing. You want to do more experiments to see if your theory holds up. The law of conservation of mass is something that's very important in the field of chemistry. The law of conservation of mass states that the total mass remains constant during a chemical change or a chemical reaction. So what this means, that if you weigh the reactants and you weigh the products in a chemical reaction, the mass before and after the chemical reaction will be equal. So this is a very important concept, as we'll see throughout this course. Now, matter is different than mass. Mass is a reference to the amount of something, whereas matter is what something is made of. There are two principal ways in which we can classify matter. We can either classify matter as a solid, liquid, or gas, and a perfect example is water. Water in its solid form is called ice. When it's a liquid, generally it's just referred to as water, and it can also exist as a vapor or as a gas. The other way that we can classify matter is we can classify it as either an element, compound, or a mixture. So here are examples of each. This is an example of an element. This is sodium metal. This is an example of a compound, sodium chloride. And this is an example of a mixture. And what we have here is sodium chloride being dissolved into water. Matter can undergo two different types of changes. It can undergo a physical change or it can undergo a chemical change. Now, a physical change is when matter changes form, but its chemical composition remains the same. And a great example is when you leave an ice cube on your kitchen counter. When you leave an ice cube on your kitchen counter, it begins to melt. It changes from its solid form into its liquid form, but its chemical composition is still going to be the same. It's still going to be H2O or water. Now, a chemical change is one in which the composition of matter is transformed into new matter or several new kinds of matter. A great example is when iron combines with oxygen to form rust. This is a chemical change, and this is the reason why you shouldn't leave your bike out in the rain. But rust is just something that occurs very naturally. When metals are left outside and exposed to the elements, eventually they begin to rust. And here's a great example. This is a chain actually from the San Francisco Bay Bridge. And you notice that the chain is beginning to rust or oxidize. And this is just a chemical change that occurs when a metal chain like this is left outside, left out in the environment. So we defined a physical change and a chemical change, and we talked about the differences between them. But now let's talk about the difference between a physical and a chemical property. Well, a physical property, or physical properties rather, are characteristics of a material that can be observed without changing a material's chemical identity, whereas chemical properties are material characteristics that involve chemical change. Now, a substance is something else that you are introduced into in an introductory chemistry course. And a substance is a type of matter that cannot be separated into other kinds of matter by a physical means. For instance, consider that a mixture of sodium chloride and water could be separated by physical means. You could always distill off the water from the solution, and then at the bottom of your solution would just be sodium chloride. But sodium chloride, on the other hand, is a substance, and this is because sodium chloride cannot be separated by physical means. Moving on to mixtures. A mixture is any sample of matter that is not pure, and it can be separated by physical means to yield two or more substances, because remember, a substance is something that cannot be separated by physical means, where a mixture is composed of two or more substances, so you can separate out those two substances, or you could have up to 3, 4, you could have many substances in a mixture, and you could always separate them by physical means. Now, when we talk about mixtures, there are two types of mixtures. There are homogeneous mixtures, and a homogeneous mixture is a mixture which has uniform composition, and every part of the solution has the same properties. So for instance, in a sodium chloride solution, if you were to take a sample from the top of the solution and a sample from the bottom of the solution, you would get the same thing. It would have uniform properties. It would have an equal concentration of sodium chloride in either part, wherever you sampled, from the top or the bottom. So this would be an example of a homogeneous mixture. And same with a cup of coffee. A cup of coffee is also an example of a homogeneous mixture. Now, a heterogeneous mixture is composed of dissimilar parts, and a perfect example is a water-oil mixture. Remember, oil floats to the top of the solution because it is less dense, and water is at the bottom. So if you took a sample here from the bottom of this oil-water solution, it would be mostly water. And if you took a sample from the top, it would be mostly oil. And this is because it is composed of dissimilar parts. The concentration of oil in the top is different than the concentration of oil in the bottom. So that would be a heterogeneous mixture. Significant figures are something you hear thrown around a lot in chemistry. And significant figures are the digits in a measured number that include all of these certain digits plus a final one with some uncertainty. Significant figures are important because they give you information about how precise a measurement is. And in order to determine the number of significant figures or precision of a measured number, there are four rules that you need to memorize. One, all non-zero digits are considered to be significant. So 123, 0.123, and 0.00123 would all have three significant figures. Two, zeros between non-digit numbers, non-zero digits are significant. So 1,203, 0.1203, 0.001203 would all have four significant figures. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and it's because this zero falls between two non-zero digits. 2 and 3 are non-zero digits. 3, leading zeros are not significant. So this number here, 0.0023, would only have two significant figures. These zeros here are not significant, just the 2 and the 3. So this has two significant figures. And fourth, the last rule, trailing zeros in a number containing a decimal point are significant. So 12.300 would have five significant figures, and that's because these trailing zeros after the decimal point here are considered to be significant. So this number would be precise to 5 digits. Scientific notation is something that you see a lot of in chemistry, and you see a lot of it in all other sciences alike. Let's say that someone reports a measurement of 2,000 centimeters. Well, based on this number, you're not certain whether there are 1, 2, 3, or 4 significant figures associated with this number. Well, a way to avoid uncertainty is to report your number in scientific notation. Scientific notation is a way to write the number a times 10 to the n, where a is a number with a non-zero digit to the left of the decimal point, and n is an integer or whole number, and n, of course, indicates the power of 10. If the measurement of 2,000 centimeters is precise to two significant figures, it would be written as 2.0 times 10 to the third. So here are two numbers, and that indicates this number here has two significant figures. Now, on the other hand, if it's precise to three significant figures, you would write the number as 2.00 times 10 to the third centimeters. So scientific notation is a convenient way to express very large or very small quantities that would be otherwise difficult to express in a decimal form. At this point, you may be wondering, how do we determine the number of significant figures to report in a measurement involving calculations? Well, very simply, we follow two rules. One, multiplication and division. When you're multiplying or dividing measured quantities, we report as many significant figures as there are in the measurement with the least number of significant figures. So let's do a quick example. If we have a sodium chloride solution, which is just NaCl, sodium chloride, in water, we find that 23.5 grams of sodium chloride dissolves into 64.384 grams of H2O, and we want to determine the amount of sodium chloride that will dissolve in 100 grams of H2O. Well, you set up a little ratio here so that your grams of H2O cancel, and you see that 36.49975 grams of sodium chloride will dissolve in 100 grams of H2O. Well, this number here, 23.5, has the least number of significant figures. It has 3 sig figs. So that means that your answer must be reported to 3 significant figures. So we would report our answer as 36.5 grams. So 36.5 grams of sodium chloride dissolves in 100 grams of H2O. The second rule is for addition and subtraction. When you're adding or subtracting measured quantities, you report the same number of decimals in the answer as there are with the least number of decimal places. So for example, the addition of 10.987 grams and 8.67 grams is equal to 19.657 grams. However, the number with the least number of decimal places is 8.67. It has 2 decimal points. So we would report this value here is 19.66 grams. So the number of decimal points in our answer reflect the number of decimal points in the number with the least number of decimal points. This has 2, and so our answer must have 2 decimal points. The SI system of measurement is something we see a lot of in chemistry. And the SI system is a standardized means of reporting measured quantities. The SI base units, like these here in Table 1, are like the building blocks of the SI system. And this is where all other measured quantities are derived from. Everything's derived from these SI base units. And so it would behoove you to memorize all of the SI base units. So for instance, for length, the SI base unit for length is the meter, and the unit symbol is M. So please do yourself a favor and memorize the SI base units. Next, we have SI prefixes. And the prefixes are added to the base unit to produce a multiple of the original unit. SI prefixes, as indicated by Table 2, are used to indicate the power of 10. And when an SI base unit is combined with the appropriate SI prefix, one can express any type of measurement. So, like the SI base units, you need to memorize the SI prefixes. From the SI base units, for standard measurements, we can derive other units, as indicated by Table 3. Now, the number of derived units is unlimited, and they are all obtained by means of mathematical operations involving the SI base units. And a good example is volume. Volume is length cubed, and so if your length is in meters, the SI derived unit for volume would be the cubic meter. Conversion factors are something that are very important in chemistry. And the reason that they're so important is because conversion factors provide a roadmap for getting from one set of units to another for the same measured quantity. For instance, let's say that we wanted to convert 15 cubic centimeters into liters. Well, we know that 1 liter is equal to 1,000 cubic centimeters. So converting from cubic centimeters to liters isn't very difficult. First, you want to set up a conversion factor, and you put the units that you want to cancel in the denominator of this expression and the desired units in the numerator. And so this allows for the cubic centimeters to cancel. And you see when you multiply 15 times 1 over 1,000 that 15 cubic centimeters is equal to 0.015 liters. So this 1 over 10 to the third cubic centimeters, and remember 10 to the third is just 1,000. So 1 over 1,000 cubic centimeters is called a conversion factor. And conversion factors allow you to convert between different units of the same measured quantity. This method also allows us to convert between US and metric units. Say that you wanted to convert 2.6 miles to kilometers. Well, the conversion factor for miles to kilometers is 1.609 kilometer per 1 mile. So you set up your expression so that miles cancel, and you see that 2.6 miles is equal to 4.184 kilometers. Well, you got to round this to two significant figures because this number here, 2.6, only has two significant figures. So the answer is that 2.6 miles is approximately equal to 4.2 kilometers. Let's talk about the basics of nuclear structure. The atomic number is the number of protons in the nucleus of the atom. Now, protons are nuclear particles, meaning they're contained within the nucleus, with a charge equal to that of an electron. However, their mass is nearly 1,800 times greater than the mass of an electron. Now, elements are groups of atoms that all have the same atomic number. Neutrons are also nuclear particles, which means they are contained within the nucleus of the atom. They have a mass number that is nearly identical to a proton, but they have no charge. That's why they're called a neutron. They're neutral. The mass number for an element is the number of protons and neutrons together in the nucleus. So the number of protons and neutrons, the weights associated with these two particles, account for nearly all of the mass of an element. And this is, again, because the mass of an electron is so minuscule compared to a proton and a neutron. It's nearly 1,800 times smaller than a proton and a neutron. Isotopes are an interesting phenomenon. An isotope is an element that has the same atomic number, but it has a different mass number. So what does that mean? Well, an element is defined by the number of protons. So this must mean that an isotope would have a different number of neutrons. Elements are actually mixtures of isotopes, and each isotope has its own characteristic mass. So if we take helium, for instance, the mass number of helium is 4. And remember, the mass number is the number of neutrons and protons contained within the nucleus of the atom. Well, the atomic number for helium is 2. So this means it has 2 protons. The mass number minus the atomic number gives you the number of neutrons. So helium has 2 neutrons, 2 protons, and if it's a neutral atom, it will have 2 electrons as well. So to sum up, we discussed ways in which we classify matter. We can classify matter by its state as either a solid, liquid, or a gas, or otherwise we classify matter by its chemical constitution as either an element, a compound, or a mixture. The physical state of matter is dependent on temperature and pressure, whereas the chemical composition of matter remains constant. Chemists classify substances by physical properties, and many of these properties can be measured. And this is why it's important to have an understanding of the correct way in which we report measurements. Now, measurement of different physical properties is really an important practice in chemistry in all sciences alike. The SI system of measurement provides us with a standardized way of reporting our measurements and allows us to communicate our findings to other scientists. Now, since Dalton's day, atomic theory has developed steadily, and it's really been the cornerstone of chemistry ever since. And the results of atomic theory have been enormous when you consider that atoms can be rearranged through chemical reactions to give us all of the millions of compounds that we encounter on a day-to-day basis.